Hello class. Today we're going to do lesson number 8, our last lesson in chapter 5. And we're going to make some changes to the problem that they're using only because I believe that they've made that problem just a little more complicated than we need to introduce this type of a problem. These rate problems, distance, rate, and time. And so I'm going to simplify that. Then I'll go back and show you really what they were doing in terms of how they managed the time and how they needed to change the units. Now it is very important that you learn that, but I feel that it's important that you first learn the concept here of how we do distance, rate, time problems. And in this particular lesson, the example that's being used, we don't want to cloud that picture as much. So there will be a slight change, and then we'll just go back and we'll just take a quick look at why they did their problem their way in terms of how they converted. But let's just read here. Several years ago, the British Royal Aeronautical Society offered a prize of $85,000 to the first person who can build a man-powered plane that could fly a round-trip course of 1 mile. The prize was won by Paul B. McCready, whose plane, named the Gossamer Condor, successfully completed such a flight in August of 1977. Now, the plane took 4 minutes and 20 seconds to cover the first part of the flight, flying against the wind at 2 miles per hour. The return trip, in which the plane flew with the same wind, took 3 minutes. When the flight was over, the designer wanted to know the plane's airspeed. And we can use the information that we have and some simple algebra to find out. So they're telling us here we have a plane that took 4 minutes and 20 seconds to go the distance of 1 mile. Or actually the round course trip was 1 mile, so it would have really been a half a mile because they have to go 1/2 the first part and returning, because imagine you're starting at point A, and here's where our minds have to now start thinking physically in a sense of I'm going from point A and I'm going to travel all the way to point B, right? And then I'm going to travel back. So whatever distance I go, regardless of whatever direction, I'm going to end up at another point, and then I'm going to return back to my original point. Now, that means that the flight, if it was 1 mile, that was a round-trip course of 1 mile, it would have then taken it would have been 1/2 a mile. Now, the half mile in itself isn't necessarily important here, and let me explain why. What we need to understand is that it went a distance, and then it went another distance, and that both distances were equal. So we really have, let's just call this distance number 1, right? It traveled, and then it traveled distance number 2. Did it not? And now that we were told it was a return trip, so these are little buzzwords that we have to pick out of our problems and the information and the words so that we can then visualize. Sometimes we need to draw an actual illustration to help us better understand where the components are so that we can better build our equations. And in this case, we're just seeing a point A going to point B, and then point B going back to point A. And we know they're the same because it's the same points, okay? So we know that distance 1 is equal to distance 2, right? So let me just put my little trusty dusty D is equal to RT up here on the right-hand side of my board, okay? That we always need to know that distance is always going to be equal to the rate times the time. Okay, so now they say that we can use some simple algebra to figure this out. We've been given a time, 4 minutes and 20 seconds. I'm going to change that time to 4 hours, okay? Now that means we're not going to convert, because ultimately if the plane was flying at 2 miles per hour, and it went 4 minutes and 20 seconds, we're going to end up with a myriad of conversions here, and that's what I'm trying to avoid. I just want you to understand how to construct the equation first. So let's just say that this distance was covered, the first distance was covered in 4 hours. I'm just going to put that over here, okay? Ooh, I'm sorry, there should be an H, and that's the R. So time is going to be here, T, 4 hours. And I'm just going to reduce this one again for the simplicity of our equation to 3 hours, okay? I probably should have given myself a little more room up here, but I need to do my problem as well. So, and we're also given something peculiar. We have the wind, and we have a wind. It's flying against the wind at 2 miles per hour, and then it returns with the same wind, which means I guess the wind is to the front because it's going against the wind, so you're kind of flying into. Now imagine what that does to an object, okay? It actually offsets. If I don't know if you've ever heard of an accident, for instance, where two cars collide. If two cars were to collide at exactly the same speed, they would both stop right in the middle. Okay, they're meeting a resistance. Okay, so it actually increases the impact. If two cars were traveling at 20 miles per hour and they had and they ran into each other directly head on, they would actually, the collision would be at a force of 40 miles per hour because it would be double. But just to understand that with science, we live in a physical world, and there are going to be forces. You may have already gone over that in science, or you're learning that in science, but things are always constantly affecting the speed of things. And so if there's a wind coming at you at 2 miles per hour, it will actually slow you down. And in this case, we're just going to assume it's going to slow us down by 2 miles per hour. And obviously, if we're going the other direction, okay, then we're going to be aided by that wind, and it could make us go faster. I think if you ever watch a football game, and if you see how when they make a decision to where they're going to kick the ball or receive the ball, and a team who gets to receive the ball, or the other team gets to say where they want to kick from, and a lot of times it's very strategic. Strategic because they want to be able to kick the ball with the wind to their back, okay? But being that the game is divided in half, and you're going to go in one direction half the game, and the other direction the other half, the strategy here is to have the wind to your back at the very end of the game. It's just a strategy that teams employ. You may say, well, why would I want the wind to my back at the end of the game? Okay, well, the reason is because if at the end of the game your kicker has to kick the ball through the goalpost to get points, to get what's called a field goal, it would help the kicker maybe put extra distance into the ball that they kick if the wind is to their back, meaning that it's aiding the ball, it's carrying. So in that particular case, you can see where science is being used to make a simple decision as to where you're going to kick the ball. So again, I'm just kind of using some examples to give you an idea of how this wind is going to affect, how force affects objects, and the wind in itself presents a resistance, and or it can actually help to propel as well. And you know, a simple example is just look at a kite up in the air. I mean, why does the kite stay up in the air? Obviously something is pushing it, and it's the wind. So let's go back and start doing our algebra. It says that if the Gossamer Condor can fly x miles per hour in still air. Okay, now x miles per hour would be a rate, would it not? Okay, and so its speed against the wind would be x minus 2 miles per hour. Okay, so I'm just going to sneak up into here. The rate is equal to x minus 2. Okay, that's the rate. If it's traveling at x miles per hour, we don't know the rate. In fact, that's what the gentleman wanted to do. He says when the flight was over, the designer wanted to know the plane's airspeed. So we're looking for rate. We have distance, right? We have distance. Well, do we really have distance? I'm not. We're gonna find out that we really don't even need to know the actual distance here. We don't have a rate. Okay, we're wondering what the rate is, and we do have time. And in this case, we change the time just to make the problem a little bit easier, okay? So time is going to be 4 hours and 3 hours. But now let's figure out this rate that we really don't know, but we do have some clues to the rate. And again, we're told that if it's traveling in still air, we're just going to use the variable x. Now you can determine that because in your problems, you're going to have things that are affecting other things. And in this case, we just have to assume that the 2-mile-an-hour wind is going to slow you down by 2 miles per hour. Okay? If you were moving, let's say 2 miles an hour, something is moving 2 miles an hour into something 2 miles an hour against it, it would just stop. Like I said, if two cars collided at 20 miles an hour, they would just like stop right in the middle. Now there's a lot more that goes into this. There's a lot of science that goes in, particularly the mass of the object. Okay, but we're just going to bypass that for now. Okay, and we're just doing this for math purposes. But again, you'll learn that more in science in terms of how mass is going to affect, because if it's a big truck that's going 20 miles an hour versus a little tiny smart car and they run into each other, I guarantee you that at the same rate, that truck is going to push that car, and who knows what it'll do to it. But anyway, let's now take a look at the other rate. If we can assume then that the speed is going to be x minus 2 for the distance, the first distance where the wind is against you, it's coming in your face, let's just say, and it's slowing you down, picture that, and its speed with the same wind, so we have x is the same wind, it's now going to help you. We're going to do x plus 2. If you turn to the top of page 226, you'll see that r, the rate, is going to be equal to x plus 2. So we've now been able to determine two important parts here. Well, you might say, well, we don't really know the distance, and though we do know the distance, let's say we didn't, okay? Let's say that we did not know that it was a 1-mile trip. Okay, we don't need to know that. And the reason being is that I explained earlier that we're going from point A to point B. And whatever that distance is, it's exactly the same as distance B to A. It's the return trip, okay? So we can now formulate an equation equal. We know the distances are equal, are they not? Well, why don't we go ahead and start formulating what might be a formula for each distance, right? The first one, we know that it's distance, so let's go from point A to B. Okay, we're going to call this AB, and we're going to say that the distance is equal to the rate times the time, right? And AB would have been, well, the distance, let's say we don't know the distance, right? So we're just going to leave it D. And we're going to say what we know is the rate, and the rate is x minus 2, is it not? X minus 2. So that's up here. And then we have time, and I decided that we'll do this in 4 hours, okay? I don't want to use 4 minutes and 20 seconds because it just creates a whole conversion issue, okay? We don't want to go there yet. We'll go back. Now, if I were to do this over here, I could do the same thing, could I not? I would have point, let's see, BA, because we're going from B to A, and I could say that, again, distance is equal to rate times time. All right. Now you're going to see how simple these things are. They can get very difficult if we don't have this general concept in our minds that one thing is equal to another thing. That's what equations are. That's the general concept, is that we're equating. We're looking at the relationship of one thing to the next. So just having that general concept, and we know that D is equal to RT, and we also know here that R is equal to x plus 2, right? So we could say D is equal to x plus 2, because we had to figure that out. And we know that it took 3 hours in this case, right? That's our 3 over here. So we've used all of our information. We used our time, and we used our rate, and well, we know the distance, but again, just follow me with this because you're going to see that we're going to be able to determine this even if we didn't know the distance. Okay. Well, what do we have so far? Well, we have two problems that have distributive rule opportunities, and we can certainly say D is equal to 4x minus 8, right? That's what we have here. X minus 2, and we're multiplying it by 4. I mean, I could just simply bring that over here. We're kind of used to seeing it over here. And then we just multiply 4 times x and 4 times negative 2, and we end up with 4x minus 8. And if we were to do the same thing here, we could do 3x plus 6. So you can see the 3, the number could be outside. It could be on the right. It could be on the left. Typically, it's on the left. We could have rewritten it and make it look easier. But now we're paused, and we're saying, well, where are we going here? I've got an x, and I've got a d, and I don't know what d is, and I can't plug it in, so I can't figure out what x is, right? Because I could sit here and solve for x, but until I knew what d was, I simply wouldn't be able to get a final answer with this, right? But there is an opportunity. First off, what we know here is that this d here, okay, down here, is equal to this d here, is it not? These guys are equal. This distance A to B, let's call it AB, is equal to BA. All right, and that's heading into a little geometry here, but stay with me. What we're simply saying is that if this D is equal to this D, and if this is equal to D, and if this is equal to D, then we can simply say that 4x minus 8 is going to be equal to 3x plus 6. Okay? Now that eliminated the d's because the d's are equal to each other. So we took two different sides, two different trips that we knew had the exact same distance. We determined what the rate and the time were, or at least formulated an expression, and we were then able to now put them both together and create an equation out of two equations, because there are really two equations going on here. We have two d equals to rt's, but we know that the d's are the same. And if they are, then the rt's are the same. In fact, in this particular case where the d is equal to the d, I could simply say that RT is equal to RT. Why? Because we know that D is equal to D. Now, it doesn't always mean that D is going to be equal to D, but if you travel a distance and you stop and you turn around and go back, and you're traveling a straight line, of course, we're assuming that, it's going to be the same distance. So in this particular case, we can make that assumption. In fact, it's not even an assumption, it's just a realization that they are equal. So now we have 4x minus 8 is equal to 3x plus 6. And here it's just a matter of doing what we've already learned, how we can handle these these terms and how we can remove them. For instance, maybe I would add 8 over here. I want to get rid of this 8, right? So I'm going to add 8. And I could do that to both sides of the equation. First off, I have to do it to both. So we would have 4x is equal to negative 8 plus 8, which is 0. And that's going to be equal to 3x plus, well, we have 6 plus 8, and that's 14. Now, we just simply have to subtract 3x from this side, right? And if we subtract 3x from this side, we have to subtract 3x from this side. And we're going to end up conveniently with just an x, which means we don't have to divide, and x is equal to 14. Now, what is 14? Well, we were covering this distance, and the distance was, well, we're going to call it 14 miles per hour, because that's the time that we were using for the resistance. Remember, the resistance was 2 miles per hour, 4 and again, so we're using things in miles per hour. And what really helped and what made this problem a lot easier was, again, using 4 hours and 3 hours of a trip. Had we gone minutes and seconds, that would have created that complexity. But here, we were able to determine that x, what was x? X would be the speed. Okay, if the wind was still, or the air was still, that would be our x is equal to miles per hour. Go back to page 225 and you'll see it right there at the bottom. It says if the Gossamer Condor can fly x miles per hour in still air, so x is equal to the rate of the speed the plane's airspeed throughout this distance. Okay, so you can see how we were able to solve, and most importantly, and again, removing all the complexities of minutes and hours and seconds, we're able to see that we can take d is equal to RT and have another equation that had d is equal to RT, and knowing that these two d's are the same means that these two are the same, and that was convenient because we were then able to remove the d here and just simply put the RT's together and solve this for x, and we were able to determine that the plane was traveling at 14 miles per hour. Okay, so that's basically what you've learned here. Now we can go ahead and put that back in, and you can see how it works. You can plug in your information and double check it. But at this point, let's see, we would then put it up here. What would be 14 minus 2 would be 12. 12 times 4 is 48. That's very good. Now we would put 14 plus 2 is 16. 16 times 3 is 48. Okay, so it was 48 here and 48 here. Those would be 48 miles. Okay, so this would have been a 48-mile trip to and from. It would have been a 96-mile trip. Okay, if the plane was traveling at for 4 hours and then for 3 hours. Okay, so we just did that to double check our problem here. So so with this, you can see again how we use the relationship of one equation to the other when we're solving these problems. Your biggest challenge is always going to be to determine what's equal to what. That's the first thing that you have to think of when you do any problem, particularly these distance and rate problems. It's not always going to be a round trip, by the way. It's going to be one thing starts and then another thing starts a little bit later. But in the end, we will know that they basically all covered, in a sense, the same distance. The question is, how do you formulate the equation? So we'll be doing some of those. So I'm going to end this video here and start up on the next part over here with the second example. Okay.